All right, let's jump right in. Welcome to another explainer, where we take these massive foundational topics and break them down into something you can actually visualize and wrap your head around. Today, we are looking at the literal mechanics of motion. Specifically, we're digging into some fantastic lecture material from Dr. Nur Ashikin Ahmad Nazri on motion in one dimension. So whether you're an engineering student who needs a quick refresher or, just someone curious about the actual physical laws that govern our universe, this is exactly where it all starts.
But before we get bogged down in the math and the physics, Dr. Nazri starts the lecture with something totally different, and I just absolutely love this approach. There's this quote by John Maxwell: "Successful and unsuccessful people do not vary greatly in their abilities. They vary in their desires to reach their potential." So often, people think understanding mechanics requires some innate, unreachable level of genius. But this is a great reminder that mastering these concepts, it's really just about your desire to put in the work. It's a complete mindset shift. You've got the ability. The real question is, do you have the desire to build this foundation?
So to build that foundation, here is our roadmap for today. Number 1, displacement, velocity, and acceleration. 2, motion diagrams and graphs. 3, constant acceleration. And finally, number 4, freely falling objects.
Okay, section 1, displacement, velocity, and acceleration. Before we can even try to calculate where an object is going to be in the future, we have to establish some basic spatial awareness. We need to define exactly what we mean when we say a body has actually moved. And in modern precision manufacturing, things like CNC laser cutters perfectly illustrate why these abstract definitions matter in the real world. Machines like this operate on strict one-dimensional axes, meaning they move back and forth along a single straight line with just incredible micrometer precision. If you're going to program a machine to cut intricate designs, you absolutely have to master the rules of one-dimensional motion. It's not just some theory on a whiteboard, it is literally the mathematics that builds our physical world.
Now, the crucial tripping point for a lot of beginners is understanding the difference between two terms we constantly mix up in casual conversation: distance and displacement. Distance is what in physics we call a scalar quantity. That basically means it only has magnitude. It's just the total ground you covered, kind of like the odometer on your car ticking up no matter which way you drive. But displacement is a vector. It has magnitude and direction. It's the straight line distance from your starting point to your exact ending point, and it specifically cares about which way you went. The SI unit for both is the meter for sure, but that directional component, that makes all the difference.
Let's actually put this into practice with an example right out of the syllabus. Example 2.1 looks at an object. Let's just call it object P. It moves 30 meters to the east, and after that, 15 meters to the south. Now, if we were just asking for the scalar distance, you'd just add 30 and 15 and get 45 meters of total ground covered. Simple enough, right? But for displacement, because it's a vector, we have to look at the straight line from the absolute start to the absolute finish, factoring in that eastern and southern direction. It essentially forms a right triangle, and you have to find the hypotenuse to get the true displacement. And honestly, that is the core essence of vector mathematics.
So let's see how this builds into our next set of variables. Just like distance and displacement are related but fundamentally different, so are speed and velocity. Speed is simply the rate of distance over time. It's a scalar. It's just asking, hey, how fast are you going? But velocity is the rate of displacement over time. It's a vector. Velocity doesn't just want to know how fast you're going, it wants to know how fast you're going and in what specific direction. Whenever we talk about average speed versus average velocity, or even instantaneous velocity at a specific split second, we are always strictly tracking that directional vector.
Which naturally brings us to the next logical upgrade: acceleration. What happens when the velocity itself isn't constant? If you step on the gas pedal or slam the brakes in your car, your velocity is changing. Acceleration is defined as the rate of change of instantaneous velocity over time. Think of it like this. If velocity tells us how displacement changes, acceleration tells us how velocity changes. It's a rate of a rate. Keeping that specific hierarchy straight in your head, that is the absolute secret to mastering kinematics.
Moving right along to section 2, motion diagrams and graphs.
Okay, so we have mathematically defined our rates, but how do we visually map them out? Humans are very visual learners, and mapping these concepts makes analyzing a body's motion so much easier to grasp. The syllabus highlights 3 primary graphical determinations we use here. We've got displacement time graphs, velocity time graphs, and acceleration time graphs. And what's really fascinating is the mathematical relationship between them. By analyzing the slope of a displacement time graph, you can find the velocity.
By finding the slope of a velocity time graph, you get the acceleration. You could literally sketch out and solve super complex one-dimensional problems just by understanding the geometry of these three graphs. It's like a giant puzzle coming together.
All right, section 3, constant acceleration.
Now, when acceleration is constant, when it's holding steady, distance, velocity, and time combine into these standard equations of motion. The source material puts a huge emphasis on applying these equations to solve one-dimensional problems. It's all about taking those foundational definitions we just learned, initial velocity, final velocity, time, and displacement, plugging them into these formulas, and predicting exactly where an object will be and how fast it will be going at any given moment. You are quite literally predicting the future through physics.
And finally, Section 4, freely falling objects.
If you take away just one number from this whole explainer, make it this one: 9.8 meters per second squared. This is the constant g, the acceleration due to gravity. The beautiful thing about analyzing freely falling objects is that they're really just a real-world application of the constant acceleration we just talked about, except applied vertically. Assuming air resistance is negligible, any object you drop is going to accelerate toward the Earth at a constant 9.8 meters per second squared. By just substituting g into our standard kinematics equations, we can calculate the exact velocity and position of literally anything falling through the air.
So, look how far we've come. We've gone from basic spatial awareness to calculating the exact trajectory of falling objects. We have built the foundation. Which brings me right back to my opening question, inspired by John Maxwell. Are you ready to test your desire to reach your potential? Because learning physics isn't just a passive activity. It requires you to actively engage with it.
And Dr. Nasri has provided the absolute perfect way to do just that. You can scan the QR code to jump into the quiz on joinmyquiz.com and actually test this newly built foundation. Because it's one thing to hear these concepts explained, right? But it's another entirely to sit down and apply them to solve problems yourself. So, pull out your phone, take the quiz, and see how well you've truly mastered the mechanics of motion in one dimension. Keep that desire to learn strong, and I will see you in the next explainer.